Let's look at Leibniz Theorem. What it is if you have a function which is a product of two functions, let's say x to the power of 4 sine x, we can write this as u times v. Yes, so here u is x to the power of 4 and v is sine x. So there is an equation to directly look at the nth derivative of y. So let's see. Let's look at the first derivative. y1 is equal to, this we know, u1 v plus u v1. Second derivative, u2v plus u1 v1 plus u1 v1 plus u v2. Now these two are like terms, so u2v plus 2u1 v1 plus u v2. Let's look at the third derivative, u3v plus u2v1 plus 2 times u2v1 plus u1 v2 plus 2 times, no, not 2 times, plus u1 v2 plus u v3. Just take it systematically, each one of these u2s, to find the third derivative. u3v plus, if you notice, these are like terms, so 2 plus 1, 3 u2v1 plus, and this, they are like terms, so 2 times this and 1, so 3 u1 v2 plus u v3. Now let's do the fourth derivative, u4v plus u3 v1 plus 3 times u3 v1 plus u2 v2 plus 3 times u2 v2 plus u1 v3 plus u1 v3 plus u v4. u4v plus, now this and this are like terms, so 3 plus 1, 4, plus this and this are like terms, so here 3 of this and 3 of this is 6 u2 v2 plus, now this and this are like terms, so 3 plus 1, 4 u1 v3 plus u v4. Okay, now as you keep observing this y2, y3, y4, y4, let's look at the coefficients first. You might realize there is a pattern. Okay, let's look at the coefficients. 1, 1, right? So let's write it down. 1, 1. In y2, 1, 1, and the coefficients are 1, 2, 1. 1, 2, 1. In y3, 1, 3, 3, 1. 1, 3, 3, 1. In the fourth derivative, we have 1, 4, 6, 4, 1. And in the function itself, that is y, we can take the coefficient as 1, whatever it be. We can always multiply it with 1. Now what does this look like? This is called the Pascal's triangle, and you must be familiar with this. Here each one of these can be generated using combinations. of permutations and combinations, right? So n C R, whose formula is n factorial by r factorial times n minus r factorial. Remember, here n is 0 because it is the function itself. This is the first derivative. So n equal to 1, n equal to 2, n equal to 3, n equal to 4. Don't forget that r starts from 0. Okay, so let's say we want to find this, the third term in the fourth derivative, coefficient. So what will it be? It will be 0, 1, 2. So 4c2, which is equal to what? 4 factorial by 2 factorial by 4 minus 2 factorial, which is 4 times 3 times 2 factorial by 2 factorial and 2 factorial. So these two gets cancelled. 2 factorial is nothing but 2. So 2 2's and 6. So surprisingly, the derivatives suddenly connects to binomial theorem. Okay, that's one thing. Now, second thing is let's look at the subscripts of the terms. Now here, if you notice, the subscripts for u starts from 1 and it becomes 0. So it is 1 0 u. For v, it is 0 1. Now here 0 means that it is the function itself. It is not a derivative. Now here u is equal to, now look at this, 2 1 0. So u is 2 1 0 and v is 1 2. Similarly here, if you look at it, u is 3 2 1 0 and v is 0 1 2 3. Here u is, the subscript of u goes from 4 3 2 1 0 and v subscript goes from 0 1 2 3 4. Yes, so which means this can be put in terms of a general formula, the nth derivative. So we can write nth derivative is, remember, we start, coefficient can be written as nc0 u n v 0, right? v0, I'm writing it, but remember v0 is nothing but the function itself, plus nc1 u n minus 1. So this keeps getting reduced by 1 and this keeps getting increased by 1. So v1 plus nc2 u n minus 2 and v2 plus nc3 u n minus 3 v3. Now this will keep going, and somewhere in the middle, not exactly in the middle, somewhere in the middle, this formula will become c r minus 1 and this will become n r plus 1 and v will become r minus 1. So naturally the next term would be what? ncr u n minus r and v would become r plus, and it will keep going, and the final term would become ncn. Just remember, you keep reducing the subscript of u and keep increasing the subscript of v. So the last term would become u 0 and v would become n. Okay, looks complicated, but it's very systematic. So this is Leibniz theorem. So given a function which is a product of functions, the nth derivative would be this. Okay, so we have seen how to arrive at this formula. But how do we guarantee, or how do we know that this would be true as we keep going forward? Fifth derivative, sixth derivative. How do you know that this would hold? So that is where mathematical induction comes into picture. Let's differentiate this. Y n plus 1 is equal to, and here the constant we take it out, times. Now we differentiate this, u n plus 1 v0 plus u n v1 plus, let's make a little bit space. Now let's take this nc1 times u, we have to take the next derivative, that is n v1 plus u n minus 1 v2 plus, now let's take this nc2 u n minus, this was n plus 1 n, so this will be n minus 1 v2 plus u n minus 2 remains as it is, and v3 plus, and shall we go one step further? Let's take one step further, plus nc3. Now we are taking this plus nc3 u n minus 2 v2 u n minus 3 v4 plus n c r minus 1 u n minus r plus 2, and v remains as it is, r minus 1 plus u n minus r plus 1, and v becomes r plus, take it slowly, understand what is happening here. Then ncr, and this becomes u n minus r plus 1 v r plus u remains as it is, so n minus r, v becomes r plus 1, and dot 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 plus, and the final term would become, now let's differentiate this, so u1 vn plus u and vn plus 1. That's the differential of this. Now we have to simplify this. Now how do we go about simplifying it? If you notice, this is equal to this, or rather they are like terms. Now these two are like terms. This doesn't seem to be matching this. Okay, what about the next? If this and this are like terms, now as far as this is concerned, this is in this dot dot dot, so that's okay. Now the only thing that is spoiling the pattern is this un minus 2 v3 and un minus 2 v2, it is coming. So let's verify that. So here n minus 3, n minus 2, v3 should come as it is. This should be as it is. So now this becomes like terms, right? So that means we can rearrange this. So here nc0 of this, no, let's first write the first term, nc0 un plus 1 v0 plus nc0 of this and nc1 for this un v1. Okay, plus now let's take this and this. The like terms are common, so this would become nc1 plus nc2 times un minus 1 and v2 plus. Now let's look at this. So here nc2 plus nc3 and common is n minus 2 v3, and we keep going like that. ncr minus 1 plus ncr, right, for this 2, and common is un minus r plus 1 and vr. Now let's look at this. That's the final term, and the previous term to this is lost in the dot dots. Okay, so we just take the final term now. So ncn u0 vn plus 1. Now there must be some way by which we can simplify this. So here again, some of the rules of combinations we need to be familiar with. nc0 is equal to 1, ncn equal to 1, and finally ncr minus 1 plus ncr is equal to n plus 1 cr. Now keeping these three in mind, what happens? This becomes 1, this becomes 1, yes, and because of this, this will become n plus 1 c1. This will become n plus 1 c2, n plus 1 c3. Okay, so let's do the substitutions. So here we are talking of, don't forget what we are talking of, y n plus 1th derivative. So this becomes now n plus 1, and let's keep this visible. So this becomes 1, so u n plus 1 v0 plus, remember this will become what, n plus 1 c1 un v1 plus, now this will become n plus 1 c2 u n minus 1 v2. This will become n plus 1 c3 u n minus 2 v3 plus, this would become what, ncr minus 1 plus ncr. This will become n plus 1 cr un minus r plus 1 and vr plus, and the last term will become 1. So u not vn plus 1. Yes. Now everything is perfect, right, except the first term and the last term, because it doesn't have this c combination. Everything else matches the pattern of yn. So let's do a trick. Look at it like this. We know nc0 is equal to 1, ncn equal to 1. That means it doesn't matter what is there here. What matters is either in the subscript you have 0 or whatever is there in the superscript. So which means we can replace it with n plus 1 c0 and n plus 1 c n plus 1, right? These two are also equal to 1, right? So what we'll do is we'll put this here and we will put this here. Then the pattern will match perfectly. Yes. So y n plus 1 equal to using mathematical induction. The theorem is proved for all positive integers, or we can write for all natural numbers. Okay, so that is Leibniz theorem. Enough for today. Bye for